the dynamic model of a pendulum is given by d square theta by dt square plus 4 theta plus t, right? Let me take another pen. Okay, let me take the small tip for pink color. Yeah, so now where theta is the displacement in radians per second and t is the applied torque, which is nothing but, you know, input. Theta is the displacement, output in Newton meter. It represents in a time scale state variable form x dot is equal to alpha x plus beta u, where alpha is called the state matrix and beta is called the input matrix. We know that, right? Now first let us represent this differential equation in terms of transfer function with respect to theta s and t of s. Okay, first take the differential equation. Differential equation d square theta by dt square plus 4 theta is equals to t. Now apply Laplace transform on both the sides. Can I say s square, assume initial conditions are not available here, s square into theta of s plus 4 theta of s is equals to t of s, right? So here what is theta is the displacement, which is the output, and t, torque, is applied, which is input. So can I say that if I take in common from these two, theta of s, if I take in common, can I write it like this is s square plus 4, which is equals to t of s. Therefore theta of s by t of s. So till this you have to do, you don't have any other option, we have to do that. So then you will get the transfer function. How is that? 1 upon s square plus 4, right? So now how we are going to represent this is in a standard form. Can we write like this? 1 upon s square plus 0s plus 4. Can I say this? Now we know that how to write the state matrix. Yeah, or here how we represented alpha. Okay, now I'll write it like this. Alpha is equals to A is equals to, you know that we will go in reverse engineering, right? With the negative sign, like change in the polarity. So 0, 1 is the first row. We know that. What about the remaining? Minus 4 and 0. Minus 4 and 0. So fortunately 0, 1 minus 4, 0, 0, 1 minus 4, 0 is available on A and B options. So now only thing which is available for us is the beta. How to check with the beta? So if you see here, is it looks like a beta, can I write directly like this? 0 and 1, right? So therefore option A is correct. 0 and 1, right? Please take this question. See, one thing, we have to first convert this is into standard transfer function form. Once you convert it into standard transfer function form, then only you will be able to solve this. Okay? Now let us see another question. Okay, so a system has the state variable representation like this. Its transfer function is, that is what they are asking. So we know that state space 2, SS, state space 2 transfer function, we know the relation. What is that? C into Si minus A in whole inverse into B plus D, which is nothing but the transfer function of the system from the state space. But unfortunately here D is not there. So D is equal to 0. What else available? This is called A and this is called B and this is called C. Only thing is we need to get this. Therefore, can I say the transfer function is equals to, can I write like this? C means 1, 1. Si minus A means S 0, 0, S, which is nothing but Si. Means S into identity matrix minus what is A? A matrix this. Iska inverse. And what is B? This is the B. we have to multiply everything. First let us calculate the inside one. So first let me calculate Si minus A whole inverse, which is nothing but adjoint of A by det of A, determinant of A. So can you tell me what is the adjoint of A? Okay, so first you write like this. Can I write like this? S minus 1 and then 0 and then S plus 1 whole inverse. This part I am calculating separately. Okay, so how to deal with this? What is adjoint of 2 by 2 matrix is straight away D minus B minus C A. What is D here? S plus 1 minus B 1 minus C 0 D minus B minus C A. This is A. Adjoint A is over. Determinant is AD minus BC. Fortunately we have S into S plus 1. Further if you simplify, what we can get? S plus 1 divided by S into S plus 1. Can I write like this is 1 by S? 1 upon S into S plus 1. This is 0. And this is, can I write like 1 upon S plus 1. Finally we got Si minus A whole inverse. Now we have to calculate this. Let me add a slide. So finally what we got? Therefore transfer function is equals to C matrix 1 1 and Si minus A whole inverse is this thing 1 by S into S plus 1, 1 by S plus 1 0, 1 by S 0, 1 by S plus 1, 1 by S into S plus 1. C into S minus A whole inverse into B. What is the B matrix? 0 and 1. Okay, just basic matrix multiplication. You do it. This is 1 row 2 columns. This is 2 rows 2 columns. This is 2 rows 1 by 1 column. So do it. This is 1 upon S. Means like finally I will get what? 1 row 2 columns I have to get. 1 row 2 columns I have to get. So it is nothing but simply inside I am writing with a different color 1 upon S and this into this. Can I write it like 1 upon S into S plus 1, S into S plus 1 into S plus, 1 upon this one, 1 into S plus 1 upon S plus 1. So this is finally 1 by 2 matrix and this we are going to multiply with 0 and 1. So you just multiply, finally you will get what? 1 upon S into S plus 1, right? 1 upon S into S plus 1 we multiplied, yes, plus 1 upon S plus 1. So simplify this, LCM is S plus 1 into S, which is nothing but 1, which is nothing but S. So can I say finally we got 1 upon S? See, S plus 1, S into S plus 1 is LCM. So here I will get what? 1. Here I will get what? S, 1 plus S by 1 plus S into S, which is nothing but 1 by S. Therefore this is the final transfer function of the system. Only thing is we have to know what is the relationship or what is the transformation between state space to transfer function and transfer function to state space, like that. So therefore 1 by S, where is that? B. B is the correct answer. B is the correct answer. I hope you understand, right? Only thing you have to understand, first apply the formula, then you need to know how to calculate determinant of. So fortunately here 2 by 2 matrix it is. Once you got the 2 by 2 matrix, we are happy. So easy to calculate the inverse and the determinant. But when it comes to 3 by 3, 4 by 4, it will be a bit complicated. Okay? Try to practice more on how to calculate the inverse of higher order terms. Okay? Now let us see next question. Okay, so now they have given transfer function. Now they are asking the state space. So what is the given transfer function? y of s by u of s is equals to s plus 6 by s square plus 5s plus 6. Okay, so how to deal with this? So can I write multiplied with 1 indirectly? Can I say that? Yeah. So now we know that whenever if we have any transfer function, so we can directly write its matrix as A matrix. How to write? It is a 2 by 2 matrix because it is a second order system. B is 2 by 1 matrix and C is 1 by 2 matrix. ठीक है ना? Now tell me from this, I told you have to go in this particular direction. Put the values with opposite polarity. So what is the standard form? Controllable canonical form only this is 0, 1. It is plus 6, it will become minus 6 plus 5 minus 5. So which we got. And for C matrix we have to go in this particular direction and don't change the polarity. 6, 1. And what else left? 0, 1. See, B matrix we got, and finally we got the C matrix as this. So immediately you can struck off this too, because the thing is C matrix should be always 1 by 2. C matrix will be always 1 row 2 columns. So definitely either this or this. Strictly speaking, output is never related with the poles. Output is never related with the poles. It is always related with the zeros. Remember, always zeros reflects only output side. It means only matrix C. Only matrix C and B also. Only matrix C and B. Only A matrix deals with this. This is deals with only. Remember, mark this word. Only A matrix. Only A matrix. So it is so easy to eliminate these options. Okay. Okay. Now let us see this question. The state transition matrix of the system with the given transfer function g of s is equals to 1 upon s square. 1 upon s square. So for this particular 1 upon s square, we need to calculate the state transition matrix. State transition matrix means e power at. E power at means L inverse of Si minus A whole inverse. L inverse of Si minus A whole inverse. So for this particular transfer function, we need to calculate the first matrix here. So can I write g of s like this? 1 upon s square plus 0s plus 0. Can we write like this? Then what is the matrix here from this? Can we write matrix here like this? 0, 1, 0, 0. 0, 1, 0, 0. So first of all, for this particular matrix, we cannot calculate the state like inverse of this matrix. Why inverse you cannot calculate? Can we calculate Si? A inverse you cannot calculate. Si minus A inverse? You cannot calculate A inverse because determinant is 0. But Si minus A whole inverse? Yes. Let's see. What is Si minus A? S 0, 0, S. Minus A is 0, 1, 0, 0. What is its matrix? Can I say its matrix is like this? S minus 1, 0, S. Okay, na? So we got Si minus A. We got Si minus A, and we have to calculate its inverse. That is most important. That is most important. S minus 1, 0, S. Let us take another slide. How to calculate Si minus A whole inverse? Yes. S minus 1, 0, S. इसका inverse निकालना पड़ेगा. How to calculate that? Yes, I told you 2 by 2 matrix. D minus B minus C A adjoint A by that A. Now, yes, tell me, can I say S by S square is? 1 upon s. 1 by s square. 0, 1 upon s. This is what? Si minus a whole inverse. But what do we need to calculate? State transition matrix, na? E power 8 is equals to Laplace inverse of Si minus a whole inverse. So, iska inverse kya? I mean, iska Laplace inverse is what? E power 8 is equals to 1 upon s ka 1, 0 ka 0, 1 upon s is 1, 1 by s square is t. So, just see which option. 1t01. This is the option. So, till now we have seen the questions which are used to calculate the transfer function from the state space and state space to transfer function and identifying the C matrix, A matrix, B matrix. But we have extended little bit above it, that is nothing but state transition matrix, which is nothing but this relation e power 80, which is nothing but inverse Laplace of. That means you have to calculate the Si minus a whole inverse and you have to apply finally inverse to this. So that you will get what? This matrix. 1 by s square ka Laplace transform is what? T only, na? Yes. Now let us see next question. Okay. So look at this matrix, which is what? A matrix is 3 by 3. Very much important, where they want to kill your time by giving such questions. 0, 1, minus 2, minus 3, minus 4. A matrix. And the B matrix is 0, 0, 2. Okay. So what they're asking, check. Okay. C also they have given. Okay. What they're asking, check controllable, observable, whether it is yes or no. For controllability, C is equals to, we know that this is the standard form. B, AB, A square B. Why we have taken A square B? Because it is a 3 by 3 matrix, sir. 3 by 3. First calculate AB. Okay, first why I calculate AB? A square let us calculate. So it will be very easy for us. A square 0, 1, 0, 0, 0, 1, minus 2, minus 3, minus 4. Again same 0, 1, 0, 0, 0, 1, minus 2, minus 3, minus 4. Okay, you just do this A square. So finally you will get 0 here and this into this again 0 and this into this will be getting what? 1. We'll be getting 1. See 0 into 0, 0, 1 into 0, 0, 0 into minus 2, 0, 0 into 1, 0, 1 into 0, 0, 0 into minus 3, 0. So that is 0, 0 into 0, 1 into 1 is 1, 0 into 4, 0. So 1 you got finally. What about this? You will get minus 2. This thing minus 2, and what about this? Minus 3, and what about this? Minus 4. And you calculate this. 4 2s are, directly we can do 4 2s are 8, and do this minus 2. Yes, 4 3s are 12. Minus 2, 4 3s are 12. 12 minus 2, which is nothing but 10. Same, do this. So you know, minus 3 plus 16. Minus 3 plus 16 means 13. We got A square here. So now problem is over. So first let me take B matrix. What is B matrix, sir? 0, 0, 2. So we have to be very quick while doing this multiplication. So multiply this. 0, 1, 0. A, B, na, next we have to put 0, 1, 0 multiply with 0, 0, 2. So can I take it 0? 0, 0, 1, you get 2. Minus 2, minus 3, minus 4, minus 8 you got. AB is over. Now with respect to A square into B. So what is A square into B? 0 into 0 into 1. 1 into 2 is 2. Minus 2 into 0, everything is 0. Minus 8. Everything is 0. 13 into 2, 26. So obviously it's determined. Once you check, it is not at all 0. You see here, I can take this is as the term. So this row, this one gets cancelled. So AD minus BC, right? So which is nothing but determinant of C is equals to 2 into, tell me, minus 4. So therefore minus 4, which is not equal to 0. So simply it is controllable. Determinant should not be equal to 0. Should not be equal to 0 to say controllable. If it is equal to 0, it is not a controllable. So out of 4 options, these 2 we can eliminate. But other thing is also there. We have to check, yes, observability. Okay, let me add the slide. Observability. O. How to deal with observability? O. This is C, CA, CA square. Okay. Already we know what is C. Already know what is C. C matrix 100. Already we know 100. And what else left? C and CA. C into A. So this you have to multiply with A. So here let me write 100. I want to multiply this with this. So 0 and entire thing will be 0. And this 1, okay, 0. If I multiply these two, what I'll get? 1 into 0, 0. 0 into 0 is 0. 0 into minus 2 is 0, 0. 1 into 1, rest all are 0, 1. 1 into 0 is 0, 0, 1 into 0, 0, everything is 0. So finally you got what? CA 0, 1, 0. Now CA square. So this is A square we got. What is C here? 1, 0, 0 na? 1, 0, 0. Multiply. 1, 0, 0. Everything will be 0. 1, 0, 0 multiply. Again 1, 0, 0. Again 0. Again 1, 0, 0. You got 1 here. Understand? 0, 0. This is 0, 0, and finally 100 multiplied with this, you will get 1. So 001 you got. 001. So its determinant is what? Can I say 1 into this and this gets cancelled. So determinant is AD minus BC 1. So obviously it is not equal to 0. It is also observable. So therefore the given system is both controllable and observable. So which option is correct? Option E is correct. Both controllable and observable. Okay. Now let us see this question. So again they are asking about controllable and observable. So what is the given matrix A? 2, 3, 0, 5. What is the given matrix B? 1, 0. Okay. So 2, 3, 0, 5, 1, 0 we got. Now we need to check whether it is a controllable and unstable. Stability they are asking. First, for stability purpose, let us calculate the, the characteristic equation. Once if you know the characteristic equation, we can get the poles of the system. Once if you know the poles of the system, we can comment straight away. What is the characteristic equation relation? Si minus A whole inverse. Okay. Or you can do Si minus A also, no problem. Si minus A. Okay. Si minus A whole inverse you do. What is Si minus A whole inverse? S0, 0, S minus. What is A? 2, 3, 0, 5. Okay. Because Si minus A whole inverse only will give you the characteristic equation. Okay. Characteristic equation. And totally whole inverse. S minus 2 minus 3 0 S minus 5 whole inverse. So better you calculate the simple determinant. Determinant is what? S minus 2 into S minus 5 equal to 0. Because we want only the denominators of this entire transfer function. What is the denominators of this entire transfer function? Is characteristic equation only. Okay. So therefore can I say S minus 1 into S minus 5 is equal to 0 means poles are lying on right half of S plane. So therefore system is unstable. So out of these 4 options, these 2 straight away we can eliminate. But only thing we need to calculate is controllability. How to check the controllability? C is equals to B AB. What is a B matrix? 1 0. What is AB matrix? Multiply 2 3 with respect to 1 0, which is nothing but 2. 2 3 multiply with 1 0, you got 2, and 0 5 you will get 0. So therefore its determinant of C is equals to C AD minus BC 0. So therefore it is not a controllable, non-controllable. So therefore I can say system is unstable but uncontrollable. Can we say this? Yeah. Now let us see another question. Yeah. Now obtain the state space representation is diagonal canonical form for the following system. So for the diagonal canonical form, first we need to write this equation: d cube y by dt cube plus 6 d square y by dt square plus 11 dy by dt plus 6y equal to 6u of t. Okay. So let us apply Laplace transform on both the sides. Then I will get s cube plus 6s square plus 11s plus 6 into y of s is equals to 6 into u of s. Okay. So from these, how to write this equation? Sorry, 6 ut na? 6. Therefore Laplace of output by Laplace of input. What is this? So 6 by s cube plus 6s square plus 11s plus 6. So remember this characteristic equation, and very much useful for you. Most of the times you can expect the same thing when you go to any TRANSCO GENCO or any PSU examinations, because it's calculating its roots is difficult because you don't have the calculator. But straight away its roots are, you can directly take this. You can check also s plus 1 into 2 into 3. But what is the representation? He is asking diagonal form. So first of all you need to calculate the partial fractions to this. How to calculate? 6 by s plus 1 into s plus 2 into s plus 3. Its partial fractions are, can I write like this, is a by s plus 1 plus b by s plus 2 plus c by s plus 3. So after solving by rearranging the equations, you will get a is equals to 3, b is equal to minus 6, c is equals to 3. So your first step, what you have to do, you have to convert into this matrix. What is that matrix? Diagonal. First of all, diagonal form means you need to first use the partial fractions. From that you can directly write diagonal form. This is the very much important model where everybody will get confused, and you should not commit a mistake on this. So look at the poles. What are the poles locations? Minus 1. Only put in diagonal form only. That is, it is called diagonal matrix. That's it. So if you observe, this minus 1, minus 2, minus 3 are nothing but poles. That's it. And B matrix, you directly take A, B, C values. What are the A, B, C values? 3 minus 6, 3. And for the C value, 1, 1, 1. Straight away we can take. Okay. So observe very carefully. Diagonal form mein there are basically 3 models. First model is, you will be getting like in a simple form. No repeated poles will come into the picture. So for that, this is the straight method. there is another method called multiple poles, or you can say repeated roots. We can say that repeated roots. If you have a repeated roots, problem again come into the picture. On the other hand, we have a complex roots. That is also another method. But as of now, for gate point of view, or you can say GENCO, TRANSCO, any PSU point of view, you will be having diagonal form only, like this directly. You do partial fractions, put the poles values in the diagonal form, rest all are zeros, and whatever the ABC values you put for ABC, and remaining you put 1 1 1. That is the matrix you have to get. Okay?